So far we looked at multilayer perceptrons, which are feed-forward neural networks that are fully connected. So in these networks we had one input layer, one output layer, and in between some hidden layers which are fully connected to the input, the output, and each next hidden layer. And while these networks are can be very good in some cases, in other cases they aren't powerful enough to solve all problems. Some of the issues of multilayer perceptrons are that they're prone to overfitting and that they can't deal with sequences of variable length, and they also have other issues. So in this video we're going to look at other types of neural networks which are built differently with different types of layers that aren't just fully connected, and we'll see in which cases they can be used to improve upon the performance of multilayer perceptrons. So the first type of neural network that we're going to look at is the convolutional neural network. So these are regularized versions of multilayer perceptrons, and they are specifically suitable for working with images. So we usually use them if we want to process and classify images. And a big advantage of the convolutional neural networks is that they don't need as much pre-processing as other neural networks when working with images. So a convolutional neural network is a network that contains at least one convolutional layer. This convolutional layer is a layer whose parameters consist of filters which slide across the height and width of the image. So these filters are fairly small, but they slide across the entire image, and they compute the dot product of the filter and the input. What this does, in effect, is that it helps the network learn filters that will then activate when they see some type of visual feature. For example, if for example, this filter can, for example, recognize edges or certain other features of an image, and then activate accordingly. So here we can see on this image, we can see what this looks like. So this yellow thing here is the filter, and we have the image here. So the filter goes across the entire image. So for example, it takes so it will first look at these pixels and then see. So this filter says we have 1 here, 0 here, then 1, then 0, 1, 0, and then 1, 0, 1. So then we look at this here. We have 1 here, 1 here, 1 here, and 1 here. We multiply those by 1. So we multiply this by 1, this by 0, this by 1, then we have 0, 1, 0, and then 1, 0, 1. And if we multiply each of these inputs in the image by this filter, we will get and add them together, we get 4. So then the next part of the image that we'll look at is going to be this part here, and then we see then we'll multiply this by 1, this by 0, this by 1, then this by 0, this by 1, this by 0, then we have 1, 0, 1. And then if we multiply them, we have 1, here we have 0, then we have 1 times 0, that's still gonna be 0, then we have 1 times 1, that's 2 now in total, then we have, actually no, I'm sorry, we have 0 here, so we still have 1 total, then we have 1, we have now 2 total, then 0 times 1 will give us 0, so we still have 2 total, then we have 0 times 1, that's we stay at 2, then 0 times 1 is 0, so we stay at 2, and then we have 1 times 1, that's 1, so we add that to the 2 and we get 3 here for the convolved feature. And then another type of layer that is usually added to convolutional neural networks is a pooling layer. And what this layer does, it splits the image into rectangles. For example, if this is our entire image here, and we split it up, and then aggregate each of these parts here. So this example here uses a max pooling layer. That means that it takes the maximum of each section of the image. So for this section here, we get the 6. For this section here, the 8. For this section here, the 3, and for this section here, the 4. This helps us prevent overfitting, and it reduces the dimensionality of the image. So, right, convolutional neural networks can be combined with other types of layers as well. So, convolutional neural networks can be feed-forward, so they can, in addition to the convolutional and pooling layer, they can contain a dense or a fully connected layer. But they can also be combined with other types of neural networks that we're going to look at now, or that we're going to look at next. So this next type of neural networks that we're going to look at are recurrent neural networks. And these networks are so the thing about these recurrent neural networks is that they allow the previous outputs to be used as inputs. So the previous right, so the outputs that we get can be fed back into the previous inputs that we've had previously. This allows the recurrent neural networks to memorize these previous inputs, and they can use their internal state as a type of memory, which will help them which helps them process inputs with variable sequence that are sequences with variable lengths. So here we can see an example of a recurrent neural network. So we have some inputs, then we have some hidden layers, and we can feed the outputs of one hidden layer back to the inputs of some layer, of some previous layer, and then we continue on to the outputs. Or there are also some recurrent neural networks where the outputs, so we can feed these outputs back to the hidden layers. So some advantages of recurrent neural networks are that they can process input of any length. The model size doesn't increase with the size of the input. The computation considers the historical information, so it can remember samples that were seen previously, and weights are shared across time. Some disadvantages are that recurrent neural networks can be slow to compute and train, and there is a difficulty in accessing information from a long time ago. So while it can remember information for a long time and use historical information, using historical information from too long ago can be an issue. It can't, so this type of networks can't consider any future input for the current state, and they have gradient problems during training. That means that during training, the gradient that's used to optimize the weights can become too small and vanish, and the network will stop learning, or the gradient can also explode and get too large, which will lead to poor performance. Short-term memory neural networks, or LSTM neural networks, are a type of recurrent neural network which solves the vanishing gradient problem that traditional recurrent neural networks have. LSTM neural networks can learn long-term dependencies, and they're suitable for learning on or training on time series and sequences. And they have set some records in records for accuracy for some problems of this type. And the last type of neural network that we're going to look at is an autoencoder. So an autoencoder is a neural network that has two main parts, an encoder and a decoder. The encoder maps the input into the code, and the decoder maps the code to a reconstruction of the input. However, when this reconstruction is done, the network only reconstructs the most important parts of the data. Autoencoders are specifically suitable for unsupervised learning. So this is a type of machine learning problem where we don't use predefined labels that we want to assign to the data, but we have some data and we want to extract some knowledge from it without having labels. It can be used for dimensionality reduction. Because during this reconstruction only the most important features are kept, it can be useful for this purpose. It can be used for image processing and pre-processing, and it can be used for anomaly detection. However, some autoencoders, depending on how the network was built, can actually reconstruct the data so well that even the anomalies will be reconstructed, and therefore they can be effectively used for anomaly detection. So all of these neural network types that we saw can be combined. So a neural network can have both convolutional and lstm layers, for example. So we can combine them, and of course autoencoders can also contain convolutional layers, for example. There are many other types of neural networks, and also different types of layers that we can use in them, and that we can combine with things we've already seen. We're not going to go into any of the others. However, this is why it was important that we learn about keras and how to use it, because feed-forward neural networks or multilayer perceptrons on their own aren't powerful enough to solve all problems that we may come across.